This is lecture 36 of Condensed Matter Physics 1. And we will be talking about electron dynamics in a band in this lecture and next couple of lectures. What you have seen so far is that if you have a band, the electrons have energy E k in the band as a function of k, and I will just make the lowest energy band. It looks something like this. This is, let us say, if I am talking about one dimensional lattice, this is the Brillouin zone and this is the band. What we want to do is, what if we apply a force on this electron? How does it move in this band? Let me just quickly recall the free electron energy versus k curve looks something like this. So, in free electrons, if I have a wave vector k, then the momentum is h cross k. The rate of change of momentum p dot is equal to the force applied, and this means h cross k dot is equal to F. This is Newton's second law. What happens in a band? So, let me just recall quickly. If you have a band in this, number 1, k or h cross k is not the momentum of an electron. Nonetheless, k is a good quantum number. That means it specifies the quantum state of an electron. So, could it be that the velocity of electron is still given by h cross k by m? I am asking that question. Could it be that v dot is f over m, or h cross k dot is equal to f? And we will be answering these questions. While answering these questions, we will also learn that in a band, when you have a band almost filled, the motion of all the electrons in that almost filled band can be represented by the empty states, what are called holes. So, we will be discussing that concept also, and then we will be using these in discussing semiconductor physics after we have discussed all this. So, before we start the development of dynamics in a band, let us just put some boundaries. So, boundaries or limitations within which we will be working. For illustration purposes, I will be showing things in 1D, but the results are general. So, number 1, when I look at the energy, this is k pi by a minus pi by a, talking about one dimension, and since k is a good quantum number, so we wish to write equations in terms of k. Number 1. Number 2, an electron will be represented by a wave packet, because that is how you localize electron. So, let us take the first point first. If I want to write k precisely and still have a wave packet, delta k should be much less than the size of the Brillouin zone. Otherwise, I will not be able to define k properly. So, we can say that delta k must be much less than size of the Brillouin zone. So, that is roughly 1 over a. That is condition 1. And if that is the case, by uncertainty principle, delta x would be greater than 1 over delta k, which is equal to a, or much greater than a. And this implies that the wave packet will be spread over many lattice sites. This means that applied field should not vary much over a few lattice sites. That is the limitation. So, let me repeat this on the next slide. We have delta k much less than 1 over a, delta x much greater than a, and applied field not varying much over a few lattice sites. And this means, if I have a wave like applied field, suppose I have E, say applied field E equals E 0 sin x over lambda minus omega t, then lambda should be much greater than a. That is the limitation we are working in. That is not much of a limitation, because if I take say visible light, that is roughly 5000 angstroms. So, the wavelength is much larger. So, we are okay. And since we are talking about wave packets, we are necessarily doing semi-classical dynamics. Then other point that we will be taking is, we will confine the motion of electrons within one band. What it means in terms of applied field? So, applied field is not strong enough to cause transition between the bands. So, what we are talking about is that if I have a lattice I have an applied field which hardly varies over these lattice size. I have a wave packet which is like this. So, this is delta x much greater than a and delta k much less than 1 over a. So, if I look at the motion in the Boulogne zone, this is the wave packet. So, you can see that k is well defined, x is well defined over a large crystal, right, and E applied is spread over many lattice sites. So, this is the limitations within which we are working, but these are not much of limitations. So, this wave packet is going back and forth. Okay. So, now we go back to what we said about the velocity and all that. So, number 1, since we are talking about an electron as a wave packet, its velocity will be group velocity. So, the velocity of this wave packet will be given by V g, which is equal to 1 over h cross d E d k. And it is not equal to h cross k by m. This is incorrect. We will be talking about group velocity, that only makes sense. Now, this result we have just written that it should be d E d k, because that is the group velocity d omega d k, which is E by h cross, derivative of that with respect to k, but this result can also be derived using first order perturbation theory. And for that, I will refer you to Appendix E of Ashcroft and Mermin. So, I would like you to read that. Okay, but that is what it is. It is a wave packet which is moving with a velocity v. Now, as I said, we are talking about semi-classical dynamics. So, I will do another derivation of this from semi-classical dynamics point of view. So, let us look at that, the connection with semi-classical dynamics, and this method is due to Wannier. This makes use of the periodic nature of E with respect to k, and it will also tell you why we are confining ourselves to one band. So, if I were to plot E k versus k, this is the first Boulogne zone, and if I were to go into extended zone scheme, then we had pointed out earlier that this energy is periodic in k. This is periodic in k, so I should not be making it here. I should rather be making it here. So, this is G, which is 2 pi by a in the case of a lattice. So, I can write E k in a Fourier representation, and I can write this as equal to summation e raised to I n G A E n. Let us see, it should be e raised to I, not G A, it should be K A, it is periodic in G. So, it should be equal to summation over e raised to I K A E n A. This is just a Fourier transform. I can write this as Fourier representation. And you can easily see, if I take E k plus G, since e raised to I G A is 1, the energy remains the same. So, this is a Fourier representation of this. So, in a band, let me make it again. Energy E k is periodic with G, and any periodic function can be written as a Fourier transform, and therefore, I have written this as E k equals summation different lattice sites e raised to I n k A E n A, where E n A is some Fourier transform of E k with respect to k. Now, replace k by minus I d by dx. Now, in 3D, it will be E k vector equals summation n e raised to I k dot r times n E n r, where r is the primitive lattice vector and n are integers. So, this n r kind of gives you all the crystal lattice vectors. Once I have written that, now replace k by minus I del. Now, I remind you that this is equal to momentum operator over h cross, but I am just doing this operation. If I do that, then I am going to have E as an operator equal to summation n, k is being replaced by minus I. So, it will become e raised to I n r dot del operating on E n r. Now, operate E minus I del on the wave function phi k r. If I do that, I have E minus I del operating on phi, the block wave function phi k r, is equal to summation n E n r, which I am writing symbolically as sum over all lattice vectors, e raised to, oh, this I will not be there, let me cut that, e raised to n r dot del operating on phi k r. This is the Taylor series expansion. This exponential is nothing but 1 plus n r dot del raised to j summation over j equals 1 to infinity. So, this is the Taylor series expansion of phi k r. So, let me write this on the next page. What I did is, I took this E k, wrote this as a Fourier series, replaced k by p over h cross operator, and therefore, E, sorry, this is not vector, this is energy E minus I del operating on phi k r gave me summation over n E n r e raised to n r dot del operating on phi k r. And this together is nothing but Taylor series expansion of phi k r plus n r. Show this. And therefore, what you get is that the energy minus I del operating on phi k r is equal to summation n E n r phi k r plus n r. And by Bloch's theorem, I have phi k r plus n r equals e raised to I k dot n r phi k r. And therefore, this thing becomes equal to summation n E n r e raised to I k dot n r, summation over n is only here, phi k r. But this is E k, phi k r. So, what you get is that if I take the energy, write this as P operator over H cross, the operator, operate it on phi k r, I get E k phi k r. So, this term out here is like the Hamiltonian of the system, Hamiltonian operator. Let me repeat. I took E k, replaced k by p operator by h cross, operated this on phi k r and got E k phi k r. And this implies E p operator over h cross, which is same as E minus I del operator, is the Hamiltonian operator for a Bloch electron. That we have shown. And now, I will go over to semi-classical dynamics and call this Hamiltonian operator H cross k, or simply H k, where now k is not an operator, but H cross k is the momentum of the electron in the band. even better, I would call H cross k is the conjugate momentum conjugate to x or r for an electron in the band. That is point number 1. Point number 2, while getting this result, we restricted ourselves to one band, because all the summations and everything were over one band. So, we are working within a band. So, these two things are very clear. And once I recognize this is the Hamiltonian operator, then I know from Hamiltonian dynamics that r dot is going to be equal to del H by del P, which is 1 over H cross del E k by del k, where writing vector means the derivative, the gradient operator, or this means x dot equals 1 over H cross del E over del k x, y dot equals 1 over H cross del E k over del k y, and z dot equals 1 over H cross del E k by del k z. Doing it this way also brings out very nicely the fact that you are working in semi-classical dynamics. You took the energy eigenvalues and showed that the k is conjugate to r, and then therefore, I could write the Hamilton's equation of motion for this electron. And again, keep in mind I am talking about a wave packet. So, this is kind of gives you another way of looking at that the velocity of electron can be considered to be the derivative with respect to k. Next, since we wrote the Hamiltonian is E p over h cross or k, then in an applied field, derived from the potential energy u r, the Hamiltonian now is going to be h equals E k. Instead of writing p over h cross again and again, I am just writing k plus u r. And we have already seen that V is 1 over h cross grad k E k, which I was writing symbolically as del E del k. And now I can write the Hamilton's equation of motion and therefore write p dot, which is nothing but h cross k dot, also equal to minus del H by del R, which is minus grad of u r, which is the force. So, I get two equations. V of electron in a band can be written as 1 over h cross del E k by del k, and h cross k dot is equal to the applied force. These are the equations for semi-classical dynamics of an electron in a band. The second equation h cross k dot equals f can also be obtained from energy considerations. And for that I refer you to Kittel chapter 8. I also would like you to keep in mind that H cross k is not the momentum of an electron, because it is not the expectation value of momentum operator. Then what does this H cross k dot equals F mean? So, for that meaning, I would like you to again refer to Kittel for meaning of H cross k dot equals F. Again, read chapter 8 Kittel. So, this is your reading assignment. I have given you the equation. I have shown you that these are semi-classical equations of motion. And what is the meaning of this? You will see when you see the meaning of H cross k dot equals F, it actually takes care of the momentum that is transferred to the lattice also. So, once you read it, it will be very clear, then we can take it up in discussions. And also read how this equation is obtained from energy considerations. Now, this H cross k equals F was obtained from the Hamilton's equation of motion, that is, the conjugate momentum dot is equal to minus del H del R. This also gives for magnetic field, if the electron is moving in a magnetic field, this also gives the equation H cross k dot equals minus E electric field plus V cross B. And what is this V? V is V group. Remember, we are representing the electron by this group. So, it is always this. So, this is the equation of motion for a block electron in an EM field. So, this is the setup. I have given you everything. Now, let us see some figures as to what happens if I do apply these equations. So, let us start. Let us take this example, and I am taking this particular example because experiments exist for this. So, let us make the band first. In the band, and I will do this in the reduced zone scheme, that is, confine myself to within first Brillouin zone. This is E k versus k. Correspondingly, if I were to plot the velocity, the group velocity, that is the quantity which is meaningful, it starts with 0, has this linear behavior, goes up and then goes to 0. This is V k versus k. If I were to plot the same thing in the extended zone scheme, what will happen? I will make it small. You would have, this is the Brillouin zone, you would have the energy diagram like this, and the corresponding velocity like this, and so on. So, this is E k, this is V k, this is k, this is k. So, you see in the band, if you confine yourself within a band, the electron moves, it has a positive velocity, but then it also has negative velocity. And remember, the point out here is same as this point. Point out here, I am making the upper energy band, I am looking at that, is same as here. So, it has this velocity, then it picks up this speed, it will repeat itself. So, this point comes here. This is how the velocity of an electron in a band changes. What happens when I apply a constant force? So, motion of an electron when a constant force is applied. Now, Newton's second law tells you that V dot equals 1 over m f, but this is not true in a band. In a band, what you have is h cross k dot equals f governs the dynamics. Of course, it goes over to V dot equals f over m in case of free electrons, but this is what is going to happen. And therefore, if I were to take an electron, say in this band, and apply a force in this direction, let us say this is the force, and let us say initially the electron is at k equals 0. So, let us say k at t equals 0 is 0. This is the time, this is k. K will increase linearly, it is a constant force, go all the way up to pi by a, and that point is equivalent to, let me write it on top, this is pi by a, and this is equivalent to minus pi by a. So, electron reaches pi by a, comes to minus pi by a, and this increases again and does the same thing again. So, this is how the electron is moving in the band. Let me show it pictorially in the band what is happening. This electron moved up, this is time, up here, and then came back here and started moving like this. Went all the way to this point, came back here. So, it is moving like this here, then comes back. In the extended zone scheme, it will keep going further down, but that does not mean much. You can always bring it back, because k plus g is the same thing. So, you can bring it back to the first Brillouin zone, and this is the kind of motion that is doing. And let us see what happens to the corresponding velocity. So, if I were to plot k versus time, this is what is happening. The corresponding velocity we had already plotted. When k is 0, after that it goes up, then it will come down, then it becomes negative and go up like this. These are corresponding points. Let me make it neatly. It will come down and go up again. This is velocity with respect to time. It is moving in one band. So, it has positive velocity, it has negative velocity. Then let us plot the displacement. When v is 0, displacement is going to be minimum. Then it goes up, becomes maximum at or minimum at v equals 0. So, this is going to go up, reach a maximum, come down. I am just making it schematically, reach minimum, reach maximum, and so on. So, it reaches a maximum height, maximum distance x max with time and comes back. So, it is oscillating back and forth about this mean position. So, what do we conclude from this? Under an applied constant force, an electron in a band oscillates back and forth. Now, the time period of oscillation is going to be equal to, in this case, the k it changes is 2 pi by a h cross over f is equal to t. Where does this come from? H cross k dot is equal to f. So, this is h over a f. This is the time period. Let me bullet this. The amplitude of oscillation is going to be equal to x max by 2, and this you can very easily show by energy considerations. Force times distance is the work done, and that should be the maximum energy possible that is allowed. So, you are going to have amplitude equals E pi by a divided by 2 f. That is going to be the amplitude, because x max in the given condition is E divided by f. And you can also figure out what the mean position is. What is the conclusion of all this? This means that in a pure crystal, electrons will not conduct when subjected to a DC, a constant electric field. Because they are going back and forth. So, what I like you to do following this, if you have understood this, is plot similar k versus t, v versus t, and distance versus t graphs for the upper second band. Now, can it be checked? Question is, can we check this experimentally? The answer is yes. Oh, by the way, these oscillations are known as block oscillations. These are beautiful experiments done on Bose-Einstein condensates in a laser field. So, what one does is makes an optical lattice, a standing wave of light in which electric field is varying periodically, and therefore, an atom put here faces a periodic force. So, it becomes like a crystal for this atom, and then you apply a constant electric field by some techniques, by chirping one of the frequencies of lasers, and then you see precisely these oscillations, you confirm the time. So, I would like you to read, I will give you reference, read these very simple to read papers and very easy to read papers, but they make these points precisely. So, references I am giving you is Phys. Revlet volume 76, 4508, 1996, Physics Today, volume 50, page 30, 1997, then Physics Today, volume 57, you have 25, 2004, and these are put in resources also. So, let me now conclude this lecture by stating that we have obtained semi-classical equations of motion for a block electron, that means electron in a band, and these are V equals 1 over h cross grad k E k and h cross k dot equals f. We have discussed the motion in the lowest band in a one dimensional crystal, and the consequence is no conduction in a pure crystal. And third, I have also given experimental papers. References where these are observed. expect you all to read them, and they are very easy to read. Thank you.